In this video, we'll go over the homework that follows the lecture introducing the concept of the interval of convergence. And as always, I hope that you watched the lecture, and let's go ahead and jump right into the homework. And here's the first question. We are asked to find the interval of convergence of the following, of the power series representation of the following function, centered at x equals -1. And first thing we need to do is we need to go through the process of finding that power series. So let's do that real quick. To compensate for this +1, I actually have to subtract 11. Now we have 4 over -16 plus 11 x plus 1. Now I'm going to factor -4 over 16. So we have 1 over 1 minus 11 over 16 x plus 1. And here I'm going to use the identity, but the identity that I'm using here can only be used when this or this, let's call it star, is less than 1. And this is where we're going to get our interval of convergence. So first thing I'm going to do is I'm going to finish the process. We have a series. We have -4, 11 to the power n, 16 to the power n plus 1, x plus 1 to the power n. And all of this is only true when 11 over 16 x plus 1 is less than 1. Now, we're going to solve this absolute value inequality. And derive the interval of convergence. X will be equal to, well, actually, there's an extra step here. X plus 1 will be between 16 over 11 or -16 over 11. So x will be between 16 over 11 minus 1 or -16 over 11 minus 1. So x will be between 5 over 11 and -27 over 11. So this is the answer. So now we're going to enter it here. And after we enter it, I'm going to show you another way, which is more superior than this one. So alternatively, we can take this as a starting point, and when you are presented with a power series for which you have to find the interval of convergence, what we do is we set up the ratio test. So we assume that this power series converges for some values of x, and for those values of x, the ratio test has to produce the ratio between -1 and 1. So this is a standard setup, and a lot will get simplified here. So this whole thing will simplify this whole thing. Negatives will be gone, 4 will be gone, 11 to the end will cancel all of this, 16 to the power n plus 1 will cancel all of this. So what we're going to have left here is the limit as n approaches to infinity of 11 over 16 absolute value of x plus 1. And since there's nothing here really depends on n, we don't really need a limit. And this is all we have. And now, setting that, because of the ratio test, that has to be less than 1, that gives us exactly the same inequality. So, solving this inequality, will give us exactly the same solution as above. However, not knowing where this series came from means we also have to go through an additional step and checking this the behavior of this power series at x equals negative 27 over 11 and at x equals 5 over 11. So when x is equal to negative 27 over 11, our original series becomes, so again, I'm looking at the original series here. Original series will become negative 4 11 to the n over 16 to the n plus 1, and negative 27 over 11 plus 1, it's negative 16 over 11 to the power n. So here we have 11's gone, 16's are gone, so we only have this left. Negative 4, negative 1 to the power n over 16, and this diverges by the divergence test. And when x is equal to 5 over 11, our original series becomes this. So it's pretty much the same thing, but it's not alternating. And again, by the divergence test, it also diverges. So it diverges at both of these endpoints. So we're going to keep these inequalities as strict. Otherwise, we would have to turn it into a non-strict inequality. So this is a more superior way of determining whether not determining, but finding the interval of convergence for a given series. So moving forward, I will do one or another one, depending on the situation. So here we're going to take out 10/4. So we have 1 over 1 plus 7x over 4. Then instead of this plus, I'm going to put minus minus. And now this whole thing becomes 10/4 sigma, and goes from 0 to infinity, negative 7x over 4 to the power n. So we have, but again, this is only true when negative 7x over 4 is less than 1. So continuing this on the left side, we can simplify the power series, the expression for the power series. So we have negative 1 to the power n, 10 times 7 to the power n divided by 4 to the power n plus 1. We have x to the power n, and this will give us the solution that we'll interpret as the interval of convergence. So the absolute value of x is less than 4/7, meaning that x is between 4/7 and negative 4/7. Now, in this problem, we are going to use the ratio test. And to set up the ratio test, we're going to set up this limit of n+1th term divided by the nth term. A lot of things cancel here. And x minus 7 is not part of the limit now because it doesn't depend on n, and the limit of this square root is just going to be 1. So the whole thing is equal to x minus 7 in absolute value. Now, this has to be less than 1. And in general, when you have this inequality, like this, it produces the interval centered at C of radius r. So whatever you have here is what we call the radius. And what we have here is what we call the center. And in our case, the center is 7 and the radius is 1. So to answer the question, the radius is 1. A very similar question. Except we have the expression in the denominator, so we're going to set up the ratio test. So we're going to take the n+1th term divided by the nth term simplify, and the limit of this radical is just 1. So once again we just have this, and it has to be less than 1. So again, this is my center, this is my radius. So the radius is also 1. We actually have to find the interval of convergence here. So continue solving. Now we have to decide what whether to include the endpoints. So what we're going to do is we're going to plug in x equals 2 and x equals 4 into the original power series and see what happens. So the original power series becomes this when x equals to 2. 2 minus 3 is negative 1 to the n over square root of 7n. This is alternating series and it converges by the alternating series test. You can verify this by hand. On the other hand, here, when x is equal to 4, we have 1 to the power n over square root of 7n. this series diverges by the limit comparison test, and we're going to compare it with this, which is a p series with p equals to 1/2, which is less than 1, so it diverges. That means that we're going to include x equals 2 in the interval, and we're not going to include 4. So in the interval notation, the answer would look like this, from 2 to 4. All right, so we have 4. Question number 5. It's very similar to the first few problems we had worked on. Here we're going to manipulate this series, this function, into a series. So this identity that I'm using here is only true when the absolute value of what I just plugged in is less than 1. And solving this inequality will give us the interval of convergence. So x to the power 8 is less than 4/15, so x will be between 8th root of 4/15 and negative 8th root of 4/15. And here it's not clear whether I should write it exactly or approximately, so I guess I'm going to write it exactly. So we're going to have negative 4/15 to the power 1/8. That's the interval. All right, next problem. We're going to first manipulate this into a power series. So 5 minus 51, it's negative 46. Now we're going to use the identity. But this identity is only true when what we plugged in is less than 1 in absolute value. So that means x plus 3 is less than 46/17. That means x plus 3 is between 46 over 17 and negative 46 over 17. That means x is now between 46 over 17 minus 3 and negative 46 over 17 minus 3. And to finish the problem, I have to do the math. 3 times 17 is 51. So here we have negative 5 over 17. Here we have negative 97 over 17. I think we have a very powerful hint over here. But in order for the hint to make sense, let's actually set up the ratio, which will later you find that it's extraneous step. We don't have to. So we take the n plus 1th term and divide it by the nth term. And simplify. We have we have 13n plus 3 factorial divided by 13n plus 16 factorial, and we have x raised to the power, so 13n goes away. We have plus 13 plus 15, so x to the power 13, which is not part of the limit now, and this limit is equal to 0. So that's the hint. The hint says that this is equal to 0. So we didn't have to actually do all this work. We could have just said, hey, this is equal to 0. Now, what happens when it is equal to 0? Well, you still have to be able to make that argument. And here how it goes. We want it to be less than 1. So we're looking for those values of x that makes it less than 1. If it is always equal to 0, regardless of what x is, that means x could be literally anything. It doesn't matter what x is. That ratio is always equal to 0, making it always less than 1, meaning that for all values of x, this series converges. So the correct answer is just all real numbers. Here again we have a hint. If you're paying attention to the hint, then you may be skipping some of the steps. But here's the series. Once again, in order for the hint to make sense, let's set up this limit. So we take the n plus 1th term, which is obtained by plugging in n plus 1 instead of n, and we divide it by the nth term, and we simplify. So in this case we have this cancels this, so we have absolute value of x plus 4, which is outside of the limit now. We have 2 to the n canceling all of this, so we have 1/2, and now we have ln of 6n divided by ln of 6n plus 6. And what the hint tells us, it pretty much says that this goes to 1. So that's what the hint says. So using the hint, we can skip all the steps and just jump right into solving this inequality. To solve this inequality, we multiply both sides by 2. And we solve it as we normally solve this type of absolute value inequalities. Now, to finish this problem, we have to take the values -6 and -2 and plug it in back into the original series. So when you plug in -6 into the original series, you end up with something like this: -6 plus 4 to the power n divided by 2 to the power n ln of 6n. So what we have here is -2 to the power n divided by 2 to the power n ln of 6n. So this just cancels out, and we are left with -1 to the power n. And this is the alternating series, and it converges by the alternating series test. On the other hand, when you plug in x equals -2, you end up with -2 plus 4, 2 to the n, ln of 6n. -2 plus 4 is just 2 to the n, so 2 to the n cancels, and we just have this. And I don't think n is right, so actually n starts at 1. I just noticed that. The reason for that, because ln of 0 is not defined. And this series actually diverges, and we can make this argument using the direct comparison test. So this series is greater than 1 over 6n, which diverges because it's a harmonic series. So we include -6 in the answer, and we don't include -2. So the final answer is from -6 included to -2 not included. And probably the last question, we have the following series. And we're going to set up the ratio test by taking the limit as n goes to infinity. We're going to take the n plus 1th term divided by the nth term. All inside of the absolute value. Simplifying, this cancels, so this cancels. We have limit as n goes to infinity of 4 ln of 4n over ln of 4n plus 4 times absolute value of x minus 2, which is outside of the limit. Previously we have seen that something like this goes to 1, so this whole thing becomes 4 times absolute value of x minus 2, and by the ratio test this must be less than 1. So this is the inequality that we now have to solve, but we know that these inequalities are always allowing us to interpret them, or some parts of them, without actually solving it all the way. So this is our center, and this is our radius. And we can see, the question here is only asking for the radius, so the radius is 1/4. We're not concerned with the interval itself, but rather just the radius. So that means we don't have to do the check. We don't have to check the points at the ends of the interval, which is good news. All right, so it looks like we have completed this homework. If you have any questions, please feel free to reach out.